All right, so be honest. Somebody asks you to picture in your mind's eye what a generic subset of the real numbers looks like. What are you going to think of? I know what I think of. I think of like a friendly open interval over here. Maybe a closed interval. Maybe I throw in an isolated point over here. You see a lot of my examples on my various videos kind of look like that, right? The problem is most subsets of the real numbers don't look like that. Most subsets of the real numbers are nasty. And so what we want to do is equip ourselves to really wrestle with that nastiness over the next few videos by looking at properties, topological properties of real subsets that let us sort of discuss the thickness of a set. How much does it resemble that open interval, which is pretty thick, right? Versus how much does it resemble a scattered discrete set of points, which is not very thick at all. So the example that I want to start with to kind of get us thinking is a set that I call an unlucky set. So how an unlucky set works is I start with a closed interval from 0 to 1. And then from that closed interval, I want to take away every real number whose decimal representation begins with the digit 7. So I want to take away everything that starts with 0.7, etc., etc. So what I'm doing is I'm just kind of deleting this little piece from 0.7 to 0.8. Notice I'm actually going to keep 0.7 because I can represent it without using the 7th digit. I can say 0.699999 repeating. So anyway, I take away everything that has a first digit of 7. And then after that, I take away everything that has a second digit of 7. And so I've taken away a little bit more. Then I take away everything that has a third digit of 7. And I've taken away just a little bit more. And so on and so on. And the unlucky set, as I call it, is the set of all real numbers between 0 and 1, which can be written without using a 7 as one of its decimal digits. Now, this is a really tough set for us to get our heads around. Let's explore why, and then after that, develop some thickness properties over the next few videos that we can apply to studying this set. So somehow, when I ask how thick is a set, I'm kind of asking the very vague question, how much set is really there, right? And so answering this question concretely is kind of hard. There's a lot of different ways to do it. For our unlucky set, for example, we start with the interval from 0 to 1, which one of the ways we could talk about how much set exists here is to kind of think of, because this is an interval, we can think of what is the width of that interval, the diameter of that interval, geometrically speaking. We could say, well, there is a width of 1 present in this interval. Now, this is a very geometric idea. It's not so much a topological one, so it's probably not the one that we're going to stick with ultimately, but it's certainly one way of answering this question. And so when I take away everything that has that first digit of 7 after the decimal point, I've taken away a chunk of these numbers. And how much have I taken away? I've taken away something that has a diameter, a width of about 0.1. So what's left over is going to be a set that has a total width of about 0.9. Remember, I've decided that I'm going to keep 0.8, and I'm also going to keep 0.7. And the reason I'm going to keep 0.7 is I can represent it as 0.699999999, repeating. Right? My unlucky set is all the numbers that can be written without a decimal digit of 7. So another way to think about it is I've taken the closed interval from 0 to 1 and I've subtracted from it the open interval from 0.7 to 0.8. And then I take away everything that has a 7 in the second digit after the decimal. And so I've taken away a bunch more chunks. In fact, I've taken away 9 more chunks. And again, I've left the endpoints on those chunks for the same reason that we left the endpoints on the first chunk. And now I've taken away some more width. I've taken away 9 intervals, each of which has a width of 0.01. And then I take away everything where the third digit is 7. I've taken away 81 intervals, each of which has a width of 0.001. And what's cool about this set, and also kind of scary about this set, is that it has this sort of fractal property to it. Right? That once I've completed this process and written everything that can be written without a decimal digit of 7, if I were to zoom in on just this interval from 0 to 0.1, it would look exactly the same as the entire interval from 0 to 1. So it has this self-similarity going on that should make us start to freak out that this set has some nasty, interesting properties that we might not be able to wrestle with yet. So if I'm using the width of my set as a measurement of sort of how much set there is, what would be the total width of my unlucky set in the limit after I remove every single real number between 0 and 1 that needs to use a 7 in its decimal representation? Well, so I started with something with a width of 1, I've taken away 1/10 from it, and then I've taken away 9 intervals with a width of 1/100th, 81 intervals with a width of 1/1000th, and so on. So the total amount that I've taken away is actually this geometric series. Right? 1 minus 1/10 minus 9 over 100 minus 81 over 1000, and so on. If I factor a 1/10 out of these terms, I get a much friendlier geometric sequence, 1 plus 9/10 plus 81 over 100 plus. It's a geometric series here with a first term of 1 and with a common ratio of 9/10. And so the sum of this geometric series is 1 over 1 minus 9/10, which is 1 over 1/10, which is 10. And so the total width that I've taken away is actually equal to 1. And so the total width of my unlucky set is actually 0. Somehow there is no width left in my set because we have shot it so full of holes that I don't have any there's no meat left on the bones by the time I've taken away everything that has a 7 in its decimal representation. And so it doesn't seem like there's a whole lot of set left after I've removed everything. And yet, we can also convince ourselves that because I still have all the rest of the decimal digits, 0 through 6 and 8 and 9 to work with, this is still an uncountably infinite set. So I have a set of real numbers that has uncountably many, infinitely many real numbers in it, and yet it is so riddled with holes, it is so Swiss cheesed by taking out all those things that have 7s in them, that its total width is somehow equal to 0. Now, width is not going to be the kind of concept that we're going to hang on to for very long, because again, it's more geometric. We want something more topological. But it does bear mentioning that this idea of width, sort of how wide an interval is on the real line, does give rise to a productive way to measure the sizes of sets that is called ultimately the Lebesgue measure on the real line, which is going to be an important way of measuring the size of sets when it comes time to define a notion of integrals later on. So measuring the width of sets is valuable in a measure theory context, but in our topological context, we mostly care about things that we can define just with reference to things like open sets or sequences and that kind of stuff, right? And so width is not going to be ultimately what we hang on to. But even just looking at the width, we expect that this unlucky set is going to be very sort of sparse indeed because its total width is equal to 0. In the next few videos, let's take a look at some topological properties that can help us to answer the questions we're trying to answer.